Hey guys, Mr. Betts here. I'd like to talk a little bit about something called higher order derivatives. And the idea of higher order derivatives is that since a derivative of a function is itself a function, then we can take the derivative of that derivative. So it's a pretty straightforward idea. That's kind of it for higher order derivatives. Now, it's not really it. It doesn't explain why we would want to take derivatives of derivatives. We've talked about what derivatives might be interpreted as when we apply uh, the idea of a derivative to an application problem. And derivatives of derivatives would also have some sort of interpretation that we'll talk about. It also gets a little more complicated when we start dealing with more complicated functions and more complicated relations, and we'll get into that with some examples. Uh, Maybe one of the more important ideas here is just the notation that we're going to use for higher order derivatives. We should be familiar with the first derivative, so what we've just been calling the derivative, but will be referred to from now on as the first derivative because we're going to be taking second derivatives and third derivatives and so on. So we can use prime notation like I have in the first two, or we might use what I call Leibniz notation, so using those differentials to indicate a rate of change. So a second derivative, if we want to stick with prime notation, we just use an extra prime. So we can do that with f prime or f double prime now, we'll say, or y double prime. If we're using Leibniz notation, it's kind of a weird notation. It's not immediately obvious why we would do this, but we put an exponent on it, and the exponent in the numerator goes in a different place as the exponent in the denominator. And the reason is we're taking the derivative of a derivative. So we should be familiar with this d dx notation, saying that we're taking the derivative of what is in the bracket here. And because of this notation, notice in the denominator, we're essentially multiplying dx times dx. Now, we're not actually multiplying them, but that it kind of has that effect. And in the numerator, we just have the d here that essentially gets multiplied by the d here. Again, it's not exactly what's happening, but it is where the notation here comes from. So to show a second derivative or a third derivative, we could say d cubed y over dx cubed. And so if we take a derivative of a derivative to get a second derivative, then we could go beyond that and take a third derivative or a fourth derivative or an nth derivative. So if we're using prime notation, we might see something like this instead of a bunch of primes. And especially if we're taking the derivative an indeterminate number of times, we want to use a variable, then we might say the nth derivative. We might also, if we're taking, say, a fourth derivative, rather than doing 4 primes, which would be acceptable, we might just put a 4 in parentheses here, and that just makes things a little bit easier to read. So this would be the fourth derivative of f. And so again, the idea is we're just taking the derivative repeatedly, once, twice, 3 times, and so on. So one other thing that I want to point out is that we can take the derivative of derivatives with implicitly defined relations. So this is an example that we've seen in previous topics. If we take the derivative here with respect to x, I'm going to go ahead and do this example. The idea is we want the second derivative with respect to x. So we'll start by taking the derivative of both sides. Derivative of sine is cosine. Leave the inner function, y is the inner function inside, multiply by the derivative of the inside, and we get dy dx equals 1 over cosine of y, which I'm going to write as secant of y. And so if I want a second derivative, I'm just going to take the derivative again. So the idea is I take the derivative on both sides with respect to x. So on the left side, I get this. So the second derivative of y with respect to x. On the right side, I'm going to use the chain rule again, using implicit differentiation. So derivative of secant is secant times tangent. But then I have to multiply by the derivative of the inner function. Remember, I'm taking the derivative with respect to x, but I have a y here, so I'm going to have to multiply by dy dx. So notice here that our second derivative is written in terms of our first derivative. So our second derivative is secant of y times tangent of y times dy dx. And the one kind of tricky thing here is that we don't want to leave that first derivative as part of our answer if we can avoid it. And we do know what the first derivative is, so we can replace dy dx with what we found for dy dx in the first step of this problem. So this is going to equal, replacing that with secant of y, we're going to have secant squared of y times the tangent of y. And just like when we did implicit differentiation, taking first derivatives, it's okay that our derivative has y in it. We might see x's and y's mixed together. In this case, it's all in terms of y. But it's not going to be okay when we take higher order derivatives to keep the lower order derivatives in there. So we want to replace those with what we know those lower order derivatives to be from earlier points in this problem. So the second derivative of y with respect to x with this implicitly defined relation is going to be secant squared of y times the tangent of y.